So yeah, welcome. I sat down and thought, if it's 20 years anniversary for Apart, it would be nice to kind of look back. But I'm old, so I started a little earlier. And so 37 counts when I did my master thesis. I did my master thesis in Erlangen, working on tools, and so it's 37 years of tools or something. And when exactly? 87 in, I think, in the summer. I need to look it up. I have it written down somewhere. Okay, so I split it up in 3 portions. The early years, which was my time in Erlangen, basically end of master thesis to end of my PhD. Yeah, this is the computer science skyscraper in Erlangen. Okay, so this is basically the time where I would still draw slides. Yeah, we had overhead projectors, and so in my beginning, basically, I was, you see still here the scribing from the pen. Basically, I draw the slides, but that was basically the time. The nice thing in Erlangen was there was a Sonderforschungsbereich, which is a German thing. It's like a special research project. It's typically a whole university, like many people involved, for 3 years, but it can be extended, and this one was so successful it got extended 3 times. So it was running from 87 to 89, but I only was part in the first 2 phases. And I worked in the work package C1, where there were 16 work packages, and each work package had 2 to 3 PhD students, so it was a huge group of PhD students, and we could talk to each other, and it was really nice. Yeah, so for monitoring, I need something special in the operating system. I went to the operating system PhD guy and say, give me that and that routine. And it was really cool. And so it translates to measuring, modeling, and evaluation of multiprocessors and computer networks. At that time, the Friedrich-Alexander Universität in Erlangen, they actually developed parallel systems. So the first system it was before me was the ECPA, the Erlangen Purpose Array. When I arrived, they were working on the DIRMU, the Distributed Reconfigurable Multiprocessor Kit. It was like 25 nodes, and reconfigurable meant you could recable the system to make it like a ring or a mesh or whatever to fit your application, and everything was done as hardware was built themselves using microprocessors. Everything was programmed in Modular 2, the operating system, everything. It was really cool. And then later, in the last 2 phases, we had MEMC, but I wasn't part of that anymore. So now coming to the monitoring part of that system, you know, basically there's different ways of monitoring. Today we're only using, because it's too costly, we only use software monitoring. Yeah? We use special software which creates hooks in the software to record things. But at that time there was also hardware monitors that really, I mean, they're still there. Basically, with logic analyzers, you could connect to something and record things. But at that time, like but also people at ETH Zurich, I know Al and Dan Reed in at CSRD in Illinois, they built hardware monitors, like boards. You connect to the system to record stuff. And so what we used was something hybrid. So you had a board with a huge event recorder, a hardware clock with 100 nanosecond to record things, but it got triggered by outside. So we basically put little hooks into the software, but it basically just wrote a value. It was basically just a store to a non-existing memory location, and then that hardware monitor would catch it. Yeah, so basically you still had the software relationships, but the overhead was basically 0. Yeah. And this is basically how it was implemented. It was a plug-in card to IBM PC. if I remember right, it was the ESA bus or ESA standard or something. Yeah, and so you see, it has a high resolution clock, 100 nanosecond. It was like 87. It could record 10 million events per second peak for if you had some bursts. But then you had an event buffer of roughly like 10,000 events, each 96-bit wide. And the idea was basically, like the stuff comes in, it's a FIFO buffer, and while it's recording, basically the PC would empty the buffer and store it to disk at the time. And then depending on, and then there was like a standard connector, and then depending on the system, you needed additional interface cards, which kind of adapted to the buses or, and so on. And so as I said, you could record up to like 48 bits with one system, or we basically just recorded less, and then you could split it up in like 4 times 12, and one card could record 4 streams if possible. And if that wasn't enough, you just got more cards. Yeah, so the PC had 4 slots. So in a one PC configuration or in a 5 PC in a one PC configuration, you could pin 4 recorder cards with up to 16 nodes to record, and then there was a measurement tick generator where there was a cable going through all these cards to synchronize these clocks on 100 nanosecond in hardware. Like there was basically a PhD guy doing the card and the necessary time synchronization protocol. And if that was not enough, you could get multiple PCs. Yeah, so the scale was when you run out of money. I think we had like like 4 cards, and we used in 1 or 2 PCs. And so it was very flexible, and just to say, basically, this is the different systems we interacted. So with a Dermo computer, yeah, where we went through a power port. The transputer, we actually had a bus adapter where we grabbed stuff from a bus. Soprinum was a German supercomputer project, some people might know. There was a 7-segment display on the front board, and we kind of connected through that. And operating system people gave us something to get some values out of that 7-segment display, and we captured from there. Yeah, and on PCs, we use the printer port, and you see other stuff. So it was very successful. The problem, my job was to write the evaluation software. The problem was, the guy who did the hardware monitor was a PhD like me, so he started at the same time as me. So he couldn't tell me what I would get. So I had to write software we got some trace data that was clear, but it was totally unclear how it would look like. So I had the idea, okay? I had a background in compiler technology, so I'd lied Lex and YAK and languages and so on. So I developed something called TDL, the trace description language. So idea basically said you describe basically how the trace looks like, and there was an interface called POET, problem-oriented event trace interface, which basically could read it according to that. And then up here you had like an interface saying, give him the next record, give him the first field, give him a value of that field, and so on. But then over time, so that was my master thesis, writing this POET and TDL. And then in the PhD thesis, I took it basically to the full thing. So I added like a filter layer, of course, with a filter language, and there were different tools, and I show you examples, and each of these tools had a command language. So everything was fully programmable to make it work. Yeah, and the name of the system was called Simple, a source-related and integrated multiprocessor computer performance evaluation, modeling, and visualization environment. Yeah, and the one thing I'm really angry about is even in 37 years, I never came up in a different way that basically the L would be the beginning of a word, but I never made it work. Yeah, okay. And here again, you see like this is much darker because this is actually 4 slides. So I had like the basic slide, which just had the monitor, then there was another slide with TDL, POET, and filtering, and one with with tools, and so you could build up the diagram like you do with animations now. In the past, you kind of like stacked the slides.
How about languages for the L, since you have all these languages? How about languages for the letter L?
Yeah, you need to think about how to work it in, but it's too late anyhow. Yeah. And that was basically the idea. This was basically the picture on all my manuals. That's basically the stream of zeros and ones coming out. TDL makes it into event records, and then with simple you get it into insight and diagrams. Okay, I probably skipped that. There's different approaches how to make with standard interfaces or something. Yeah, so I had this trace description language. Another one was basically up here where you had a standard interface, but with a standard format with self-describing. So there was, forgot the name of a self-describing format, but it was part of that Pablo system from Dan Reed or something. But the problem was you still had to write these special, like you had to, your monitor system had to create that, yeah? And so if you had a trace coming from somewhere else, you would have to convert it into a self-describing format before that tool could use it, yeah? And with my approach, I could use anything, just writing the trace description language. So this is, as I said, this problem-oriented interface. Yeah, the idea was you have a trace which could be, could have multiple segments. A segment had records and the record had fields. And then here, this problem-oriented interface, you init it with that description file. You got info about like which fields are available, what are the names and so on. And then you could move, yeah, like next record back and forth, field back and forth. And then once you had a field, it decoded it and you could get the values. So that was basically roughly the way how this poet works. And then I added this trace description language to make it readable. And like here's a simple thing. You have like a 1-byte event, a 4-byte timestamp, a 2-byte parameter. And then you say, yeah, like the byte order is this way or this way. Then there's a token field, which means it has a fixed set of values. The name is event, 1 byte, these are the values, and the interpretation of the values is that. Yeah? And then time, name is acquisition, is the time where the stuff was acquired. It's an unsigned 4 with a resolution 100 nanosecond. It's a point in time, not a duration. And then if it's in the iteration step, there's a 2-byte parameter iteration number. Yeah, so this is how it, but it could be very, very complicated. So basically, there was the trace description language, and the language also said very specific names which are like standard names, predefined. Yeah? So when you named a field event, that was the thing which caused the event. Acquisition means this is the time the stuff got sorted. And so there was a few predefined ones. So you had like semantics, what this means, and you could work through it. Yeah? This is like this filter looks like. Yeah? You had different modules, and then you say like here, you had a counter, then you basically, the first filter is search. Then you look for something, the event program start and processor master. When you find that, then it gets passed on. Before that, it got ignored. You set number of programmer to 1, and then you switch to program only. And then here, basically, you count. And when you find the last program event, you exit. And then this basically would only give you the events from program start on the first processor to program end on the last one. And so you could filter things out you don't like or so. Then you had things for checking the validation of a trace. There was a simple one, check trace, and then varus, you could specify things, yeah, like assert that the number of iteration start events is the same as the number of iteration end events, or that the iteration number is increasing by 1, and by this rule, you run it through, and the tool told you everything is fine, or you print it out with errors. Yeah. Or you had trace statistics. You can say, give me the frequency of something, or the distance of something, or the duration of something. So it's here's actually the kind of the language, and then you either got like it out like this, or you could get that summary also plotted as box plots or something. So then that was actually finding complex events. I had like a event division language, so everything iteration start, followed by many iteration steps, a potential sync, and then the iteration end. And then again, it looked for this like regular expression, event pattern, and when it found one, it printed the duration and how many it found, and so on. So that was kind of, again, this was like, I would say 90. It was like a really, really early form of a timeline diagram. Because like the presentations didn't have colors or something, so I used not a color bar, but basically different heights of a line, basically, to indicate the different events. And I just basically used a pen to color them here for the slide, but normally the printout was in black and white. So you can generate like this diagram by saying, I want to have it for all processors. These are the kind of levels you want to have. And then here would be a list of events who started that state. Yeah? And you see basically say, I want to have the resolution and the thing. And you could have diagrams like this one, but you could also have an activity diagram which would draw these start end, or you had a counting diagram that could say like go up and down and so on. It was really nice. The next thing we did is that I want to get even further. And then, so there's these data analysis packages, and at that time there was something called package S from AT&T. Meanwhile, there's a public domain version of that. It's called R. People know that, but at that point it was commercial and you had it from S. And so what I had is basically you could load the trace into the package, and then basically every field was a vector with the values. Yeah, and because it's a vector, whether you has used R, yeah, you say basically, yeah, I want to have the time where the event is relaxation end on the processor master, and the begin is the time where the event is relaxation begin on master. This gives you two vectors of time. When you subtracted the two vectors, you get a vector of durations and say, draw me a histogram. And this was not a database, but I mean, you had the full R system to evaluate it. And then the really last thing we did in the end was actually Windows started, X Windows. There was X10 at that time. And so you had a language to describe an animation. You basically say, here's a graphic object, and when that event is coming, move the object, change the color, destroy it, make it larger, and things like that. So here this was this experiment, like the different processor of Dirmus in a ring, and here the different symbols showed which phase of the algorithm the language is in, and when you know multi-grid, you go down with up and down the grids, and so in this space, he said where you're currently in the grid, and then you could run it and can watch it. So it was a very powerful thing, and I liked it very much. So, but now looking back after all that, so basically, yeah, I told the successes and failures. So what worked and what didn't. Yeah? So what really worked was really nice with this hybrid instrumentation. That was amazingly nice, and I wish we would have it now, because the overhead would go down dramatically, but no one can afford building this like this hardware monitors anymore. It's just like for our system, you would have to get thousands of cards and yeah. So we had this really advanced Zähl Monitor 4, which was actually a name, because there was also Zähl Monitor 1 to 3, it's counting monitor. And then my framework, and it could really, as I said, by changing the description, I could read software traces, hardware traces. Everyone know a Lanalyzer, which was basically you plugged it into a network, and it recorded all the packages on the network, and then I would describe the structure of a package, and I could use my stuff to basically analyze these network packages, or log files, or simulation outputs. It was really, really powerful. As I said, the problem was it was just too expensive for a larger scale. And then it really turned out it's a nice system, extremely flexible, but the only person who could use it was me. Yeah, because no one knew basically how to write, as I said, each of these languages was a manual like that. Yeah, and it was just too complex. So what we typically did, and I saw actually I have it, I think there was I thought I had a slide. Oh yeah, the slide with the monitor. It said we sold it to IBM, Siemens twice, and in China. And what we did there basically, so we set it up for their system, and I wrote them basically. So this is the trace description. This is a certain typical filter. This is the typical Gann diagrams you want to have. So we could use it like a preset things of analysis. And then over time they say, oh yeah, I want to have an additional line, or they could modify by that. But just that someone would download it, read the manual and use it, it was basically way too complicated. But the biggest problem was, you look at the data and something is wrong. You never know, is it now something like the application you monitored was wrong, or somewhere in the description there's an error. Yeah, especially, I remember with IBM, we had a protocol stack. It was the first version of ISDN where we transferred a file from here to here and then recorded it, and we had this animation where the packages move the network stacks. And we saw something at some point, the package went in the wrong place. So we didn't know, was it really a problem in the network stack software or our, 300-line animation description, yeah? And so this is, yeah. I'm still proud of the whole thing, but yeah, I never used it after that. It was just too complicated. Okay, next time after my PhD, I met Alan Maloney, some people might know, and I went to the University of Oregon, which is the computer science building, and I was there for 3 years, 93 to 95. And the context here was, I was working on a ARPA-funded project, PC++, parallel C++. This was a data parallel version of C++. Again, early 90s, many people worked at that. It was an interesting time. There was 2 parts. There was one part led by Dennis Gannon in Indiana, which basically did the language and the runtime system. And there were 2 postdocs there. Pete Beckman, some people might know him. So he built the compiler and runtime system for PC++, and it used some compiler technology called Sage++, and that was François Baudin. He was at that time in France. And then I was with Al Maloney and Jane Cooney in Oregon, and we basically did a tool environment basically for that, and we called them Tau at some point. So the inventor of Tau is me, also of a name, and yeah, you'll see. So just basically the idea here is, in a normal C++, you have objects and you have methods you can call on an object. And here in parallel C++, idea was you had special things called collections, vector, list, and so on. And when you would make vectors of objects, and it's a little bit high-performance Fortran, HBF oriented. We had align and distribution objects, and then if you called a method on it, it would basically call the method in parallel on all the elements of that collection. That was basically the idea. Yeah, and Sage++ was this kind of parser interface thing. So as I started out, I called it Tools Are Us. This was the original name, Tau, Tools Are Us. And, but when we wrote the first paper in '94, Al said, it sounds like Toys R Us, and people could think it might be a toy or something. So we renamed it to Tuning and Analysis Utilities. Yeah, and that was the original logo. And of course now, it still exists. It's not anymore a language environment just for PC++, but it's a very sophisticated thing. And we call it the Tau Performance System. But the logo is still there. So I can claim that I invented kind of the Tau name, the logo, back that. And we had a small group there. We called ourselves the Paradox. Like all the football teams in the different colleges, they have names, and the football team in Oregon is the Ducks. And so we called ourselves the Paradox. And I took the logo and replaced the football with laptop. And this webpage still exists. You find some old pictures from there. Al dancing on a party in 1994 and supercomputing stuff. It's like, it might be worth visiting. Okay, this was the whole environment. So there was, basically you get your PC++ file. Oops, sorry. No. Here. So your PC++ file, basically was a class library, basically the runtime system. You compiled that, potentially instrumented, and then you got this executable file you could run. And then basically you could either, it gave you data about itself, profile data or traces, like now. And then you had this whole set of tools around it. Yeah? So there was a tool called Cozy, which basically was the manager. You could start and launch program and things. When you had static tools like a file browser, a class browser, and a call graph browser. When this was kind of a timeline display, easy, Racy was the profile display, Breezy was the debugger, there was a performance tool, Speedy, and then you could also convert with traces. Yeah, and so I don't know. It was the next fun. Basically, I called every tool with a positive acronym. I had a lot of fun coming up with all these names. Yeah, and there was even more crafty, tandy, geeky, and yeah, whatever. Yeah. The fun thing is, even at that point already, when you worked basically with a PC++ system, you could work directly on the system or remotely. Yeah, basically you had it on your workstation and you would connect to the Paragon, whatever, in Portland, and you could control from that interface monitoring running remotely. So even that was already built in. I said, this is from 95. It's quite a while ago. One thing at that time was in Tau, it's no longer in there. It has this huge set of tools, but they were interlinked. And I got inspired, 1993, the World Wide Web was invented. And I really liked the thing with the hype, like you could click on it and got to the next page. So I implemented that in my tools. So basically, I had these hyperlinks. So you selected in one display of any tool, like a file, and then or a function or a class, and then all the other tools would kind of focus their display on the same thing. And this way it was interworking. Yeah, and I have, it basically was like that. So you had basically the profile, which is, you might remember, it almost looks the same now in even modern Tau. So this is the stuff who survives. The profile display tool, Racy, basically, this survived in some form. But all the other stuff left. Then when I selected that function here, so this is like a function, like how much time I spend on a different function. Basically, this function in Tickle got selected. When it called a function local select function of that same ID, which gives you a distribution of the function on the different nodes. And then for each tool currently running, it also basically sent, please also select the function. And then like the source code display showed the source code, the call graph display highlighted where the function gets called. And so it was really nice, interactive. And here just how this stuff looked like. This was this control panel. You could say, yeah, I want to like make something run, and then you got the output here, and start the other tools. This is how the source code browser looks like, the call graph browser, class hierarchy browser. Then this was the profiler, yeah, and it collected information on every function and method, the duration, inclusive, exclusive, a number of calls, and for each PC++ collection, it recorded the number of local and remote accesses, because you want to, of course, get the number of remote accesses low, because this is an overhead. And then basically you got this output, and when you carefully look at it, it's almost from the tabling and something, but when you use current Tau, 25 years later, it still basically looks like that, without the collection stuff, of course. So this is another thing which survived. Yeah. And this is the profiler, as some people might remember it from Tau. This was the simple, so we converted our internal trace format to RLOG, which was a tool upshot from Argonne. X Windows, you could look at it, but we also implemented a simple tickle decay event browser, like a pre-version of Vampir, so if you want, or Bavaria or something, very simple. This is something I found, and I was surprised, and that's for Felix. We had a tool called Extra P. But it was doing a different thing. So it was basically more a dim and mass. So you ran on a single core, but a multi-thread execution of a PC++ program. And when it did with some models, an extrapolation, how it would run if you had multiple processors. Yeah, but it had to do with modeling, with prediction, and we called it without a minus, but it was 95. Okay. We had another tool called Speedy, which was basically, you could say, run a program, yeah, like with different number of processors, with different other parameter, and it would run the thing multiple times, collect it, and then take the execution time and plot it. So you could get speed ups over time automatically or something. It was like a nice set. This is the systems we supported, and people who are older remember, like in the mid-90s, there were these kind of explosions of architectures. Yeah, it started with Intel Hypercube. Was it Hypercube? I think. Yeah, and E860, and but then when we had this Kendall Square, the cache machines, KSR1 and 2, sequence symmetries, SGI Challenge and Onyx, the Convex SPP, the BBN Butterfly, and then distributed system, Thinking Machine 5, Intel Paragon, IBM, SB1 and 2, Crate, T3D came out at that time, Mako, and workstation clusters with PVM and NPIN and things. Yeah, and it's actually a funny side story. So we try to make our PC++ run on all this system. And of course, it took a while to get an account on some system somewhere. And typically, once we had it ported, about half a year later, the company went bankrupt. So basically, in this project, it was a race against time that we could port to the machine before the vendor went bankrupt.
Is there some causal effect?
No, I don't think so. No, there was not like that. But it was more from us, as that we had to work hard to say, oh, we have a port before the systems was unavailable. But it was really fun. The thing is, you could run the same PC++ program. You had to recompile it, of course, to get the different runtime systems. And it ran on all these without changing anything. So it was performance portable at that time. The thing was, especially on the distributed memory systems where you had to send data over, it was portably bad performance. But it ran, yeah? and I was very proud. And then basically at the end, we had a collaboration with a Portland group, PGI, we were in Eugene and they were in Portland. And they had a high-performance HBF computer, PG HBF. And they talked, can we kind of work together? So we changed it that basically they had an instrument, like they still have it in a compiler, basically. You can say instrument that program, and when we implement that, and the output was when our trace and profile format. So you could run an high-performance Fortran program from PG, compile it, and then use the profile tools and some of the static tools on that high-performance program for us. And so that was the first step where you say, okay, use some of this technology outside of PC++. When I left, but when a little later Samir came, I said, okay, when I worked for HBF, why not just also working for C++ and making work for this and make for that and that, blah, blah, blah. And this is how basically Tau started. Yeah? And what's kind of left over is the logo, the profiler, and the profile display. But, so again, what worked here and what not? So I think it was, for that time, it was an early, fully featured Perl program environment, completely with profiling and debugging, very portable, worked very well. You just basically said, make on the tool, it ran and analyzed. It was 3 buttons. It was really, I think that's way easy to use. I learned from that, my last experience, it was called simple, but wasn't simple. And it has this nice thing with these hyper tools. And as we learned, and we know now, yeah, it was built for PC++, but it was easy to retarget for something else. I don't know whether people install Tau themselves, and it has this really weird configure script. It's not like a GNU autoconfigure, but it's some self-written shell script with just some complicated things on make files or something. I created that. I think it's one of the most innovative and simply working configuration script, but other people call it like some of the worst configuration, so I put it in the undecided thing, so depending on which side you are. But if someone wants to complain how stupid this configuration system is working, you can claim it on me. It's not Samir's fault. What really also didn't work here is, in order to make this really integration work well, you had to have parsers. In C++, it was 92, it didn't have, like, it was as complicated now, but at that time already, it was already too complicated to implement a parser as a university project. Now you can use LLVM, but this is like, I don't know how many people working on it. But as a single group, you'll never be able to do that in other languages. So this is why it was hard to kind of also get these static stuff into Tau in later. So he tried with his PDT, yeah. And also traces were kind of second, language or second level. So we already had convert and use external tools. We didn't build on that. Okay, so then I moved to Jülich. It's a funny story. I don't want to tell it now, but if you want, you can ask me in the afternoon after lunch. And I went there in '96, and somehow I got stuck there. So I'm over 25 years now in Jülich, at the Jülich Supercomputing Center. This is for people who don't know it, it's like a national lab like Argonne. It's a Forschungszentrum Jülich. It has 6,000 people, square miles of building, 40 different institutes. And I'm in the Jülich Supercomputing Center, basically a computing center there, which is a national computing center, a center for the lab, and also a Euro HPC center. The context here was we started to think about automation of analysis, and we call it either automated or the automatic trace analysis. And so we, together with Michael, he was also there in Jülich at that time, we thought, like, let's get some people together, and we funded EU working group. So we got some money for meetings and travel, and we called it APART, automatic performance. This is resources and tools. Yeah, real tools or resources and tools. Yeah, and this basically, this was '99, and so we call this meeting 25 years of APART, because we got some of the people like Bart, Brian, Eduardo from that time back together. It was actually a larger group. It would be nice to have a separate talk on that. There's a lot of stuff was there. We had an APART test suite, the bottleneck description language, and all the other nice stuff came out of it. And then later, with Felix, who was also here in 2006, Felix got funding for this Virtual Institute High Productivity Supercomputing via HPS. It's also still alive. It's actually very alive. We just get new partners, and we kind of took over this group of people and getting people together working on tools, making training, which Brian will talk later about it, and so on. And as part of that, we in Jülich, we developed two things. The first was the first kind of automatic trace analyzer called Expert. And it was in a tool environment, KOJAK, like the detective who looks for you for the bug for you. And I made this nice logo for a few years, but then I got contacted by the lawyers of Telly Savalas that I should refrain using his thing, and so we made this logo later. And the website doesn't exist anymore, but thanks to the web archive, there's the, how is that called? basically a place on the web. It collects all the web pages and stores them. And you go there, look for that URL. You find the early, like from apart, and from there you still find the old web pages and can look at it. It's nice. And then over time, of course, because the analyze itself was just a sequential program, at some point it took too long. So it basically, you made a measurement and it took like a few hours to do the analysis. So you couldn't use it in a training or so. So we parallelized that Scalasca. But this is basically the work of Felix. So like this was his master thesis, and PhD, and then basically, and he was a young investigator. Basically, his group with people in Jülich, he created Scalaska. So I will not talk too much about that. I leave it to your talk this afternoon. What I want to talk a little bit about it is basically, I found some old slides. At that time, it was 2005, we had like PowerPoint already in slides, so not our slides anymore. And this is how some people might remember how I try to motivate to other people what automatic trace analysis is. So we have this huge amount of measurement data, you do some analysis which adds derived metrics and you get even more data. Yeah, and then you have all these tools on top of it, which gives you all kind of things. And of course, they have context menu, say like switch to that mode or something. So you can get even more displays. So the poor user has to do that, and it kind of get crashed by that. Yeah. And so our idea was you take this huge amount of measurement data, it stills it down to the relevant portion, yeah, which is so small, yeah, and that you have a simple display, yeah, simple as 1, 2, 3. It has 1, 2, 3 panes, and I show you more about it. And so the user can chuckle it nicely or something. So that was my motivation always, and so. Yeah, and the idea was that was for the standard cases, yeah, like yeah, you have a clear bottleneck or 1 or 2 clear bottlenecks for normal users who have some training, and they can do that, and it's a starting point for experts. Yeah, you run it and tells you, oh, are these obvious problems in it? If yes, then I can go deeper. Yeah, and you don't have to waste time using complicated tools just to check whether something is wrong. And then, if necessary, there will be always some things which the automation doesn't capture or some really tricky cases. You can still use the tools then, but then you would get an expert, yeah? Basically, and then basically it would help the user navigating these tools. But basically, because all the standard cases are covered, the expert can concentrate on the tricky stuff and on the interesting stuff. And this was later made it into the Center of Excellence POP. Yeah, ideas that you can go to POP and you can apply for performance assessment, and Brian will probably also talk a little bit about it. Yeah, and that's basically, it's the famous slide. It's from Felix, I guess, and it must be from his master thesis, so that was kind of 92 or something, 91 or 92. It was... crystal growth allocation, and so here's was a screen dump from that. So we have this routine velo. All but the last processor is basically the last processor is done earlier. So he goes into the receive early and waiting for that send, and then he wastes all that time. And this is this famous late sender, which we started, but we of course have other things. And the idea is basically you have these predefined situations where we know something is a problem, it has a name, and for each of these problems, we say, this is the time you waste on it, and so this is the severity, how bad it is. Yeah? And then basically the tools would look for these patterns and tell you how many patterns it found, and the amount of compute time you wasted because of that, and where it's in the source code. This is basically how these KOJAK and Scalasca tools work, but Felix will probably tell you more about it. Because it's the timeline from Vampire. But It's another, it's a tool also invented in Jülich, and now it's a tool you can buy from Erlangen-Nuremberg's Wolfgang Nagel, who was my advisor when he invented it, and he became professor in Dresden and took it with him. And yeah. So yeah, that was helping. And then they said it can do more complicated things, yeah, like waiting at barriers, or here, say here you have a late sender, and you find when we look for, is there another message sent to me, but from a different processor, but early than the other one. So if you would have switched it, like first wait for this message, then that, it would have been faster. So we call it late sender because of wrong order. So the pattern can get more and more complex, and the more complex they get, it gives you more and more information what is wrong. Yeah? Then basically, and that's a portion I want to talk about, is how do you give this data to the user? And the idea was basically, we have information, like different metrics we calculate, yeah, like simple things like duration, number of calls, but also time in with patterns for a call tree and for every process and thread on the system. So it's 3 panes and 3 dimensions. Each of them is hierarchical. Yeah, like the call tree is natural hierarchical. The system tree, you have a system out of nodes, out of processes which contain threads. It's again, it's a hierarchy, and the metrics can be also in a hierarchy arranged. Yeah, and then this is basically how it looked like. Yeah, so basically you had a node that's closed, so 100% of the time is spent in main, and when you click on it and you open it, it says, okay, these functions get called from main, and then the time up here changes, so it only shows the exclusive time, and here it shows the inclusive time. And the color indicates, like the more red is, the higher the values, you quickly find it. Yeah? And so basically, this is basically how the tool looked like. So this is from 2001. It was at that time still implementing tickled decay, but basically, Python decay, you're right, Python decay, because the expert was implementing Python. And as I said, very simple trees, you had the execution time, and then inside MPI, you had communication synchronization, and then inside collective and point-to-point, we had these late receiver and other patterns. Yeah? But basically, that basically was there already 2001. Yeah? It didn't have any, like, lots of menu buttons up here and context menu something, but the basic tool was there. And what basically I want to show you in the rest of my time is basically how that simple thing developed over 25 years. Yeah, so 2003, you got like a file where you could open new files and close, and it got a little bit more complicated. And then basically I said, here, this is the property, we call it performance properties. This was language from apart over different metrics. Basically, where is in the source code, in which context, and the location over the different systems. And then basically, this is 2007. We worked together with IBM. And the problem is when the Blue Gene, like L at that point, we could use at IBM had 8,000 processors, and that list with the nodes or something got really, really long. So you couldn't look at it anymore. So what we invented was basically showing basically because it was a torus, basically the three-dimensional structure of a system. And then basically each of these points here was basically the processor. So you would see the distribution over the machine, but you could also see the neighborhood things or something. So it was really nice. So that basically was added in 2007, but it was a separate display at that time. In 2009, we said, oh, why not just use the system topology, but you could also use a topology of internal MPI topologies. Yeah, you can have Cartesian topologies inside MPI, and here, like it's from Mohr, famous weather. Is it weather or climate? Weather, yeah. And it's like here's a simulation on measurement on running a simulation of weather on Europe, and you see basically here the distribution, say, okay, like the load hits in this function, how we got distributed, and so like all the processors who work on ocean have low number of these misses and the other one high and so on. This is basically now current model, but later it got integrated, and you see here now we have much more buttons up here, and I can tell you there's lots of functions here, and when you get context menu, you get another 10 functions, and here we have different topologies, and you can switch them, and you can still get the list if you want, but and all kind of other visual displays here. So that's basically the more or less the current version. We also, in Scalasca stands for Scalable Analysis of Large-Scale Applications. We always try to really want to show how scalable the whole thing is. Yeah, it still traces, but because the analysis is done in parallel, and you don't have to kind of try to visualize the trace, you can look at really large traces. So in 2010, we broke that was basically the largest one we could do at some point, Blue Gene P, with 300,000 processors, and there's a nice paper describing everything if you're interested. And just to give an idea, so we instrumented Sweep 3D, we ran it for 10 minutes, and with 10 minutes of runtime of Sweep 3D on the 300,000 processors generated 7.6 terabyte of trace data, which sounds a lot, but these systems are built for handling this large stuff, yeah? And so you have to, at the end, you write it, and when we start our parallel analysis, you have to read it again, because there was no simple way to kind of keep the stuff in memory. And then reading and writing of these 7 terabytes just took 4 minutes on that machine. It's not much, yeah? So you ran it for 10 minutes, 4 minutes reading and writing, and then the actual analysis was in 11 seconds. Yeah, and it was 510 billion events. But just to give you a thing, basically, how much you still can handle, and you get full results, you can look down, you get basically for each of these routines, you can know how many cache misses or whatever you get on that thing, on that call path. It's fully scalable. The only thing you lose is the time. Yeah, like I mean, we still have a trace available, so if you would know where to look for, you could visualize the trace in a specific portion. The data would be there. Then this was 2013, we broke the 1 million barrier. It was on a Blue Gene Q then, and that was, don't remember what the benchmark was, but it was some sort of benchmark. PTM set. It was PTM set, a NASPARL benchmark on 4,000 nodes with 64 OpenMP threads each. We get to just a little bit over 1 million. And then a little bit later, all that work was done, was too fast, was done by Brian actually. And then 2013, we invented plugins, so you could have additional analysis which could be loaded into the Cube tool. And we used it for analyze phase profiling data, where basically we got a profile for each iteration of a loop or something. And then you could look basically how the time over these instances and threads are distributed, or you could see it as bar plots. And then as part of a DFG project, Catwalk, it was the early ideas of extra P or things for modeling what Felix was doing, and it used, I think, some code from Cube to basically say, now I use it to do the same thing, but instead of showing the metrics, now you had these functions basically, which on these points, and you can visualize them. But Felix can explain it better, and you probably have it in your code. Yeah, and then that is the, I don't know, I call it the world record, because there's probably some people in some undisclosed locations did some measurements on larger systems, but the only measurement which was either published and written about and talked about was our measurement on the full Blue Gene Q, which had like 500,000 cores, but each core could run 4 threads. So we get to 1.8 35,000 threads that we measured. Yeah, and it was a core benchmark. And you can see it says an OpenMP, and you still can find out, oh, here is some problem here at that critical inside here, and the distribution over these different processors of that critical, and so it really scales to that. I always wanted to go higher, but we never got access to these like 8 million or 10 million systems just for running some benchmark and get another record. And now it's actually going down. With all the GPUs, there's actually less nodes. And so I'm not afraid about scalability in the future for Scalasca and Scorpy, because like a few tens thousand with lots of threads and and cores on the GPU, we can easily handle. The problem is always the amount of memory available per node. And these get really, I mean, at that time it was really limited on the Blue Gene Q. You had 4 GB for all the 64 processors. Now you have like almost a gigabyte per core or something. So, yeah. Some people might say, okay, it's Brian, he knows how to handle it, and normal people can do that. But we had a guy, Itaru Kitayama in Riken, who installed stuff on the K computer, and he ran it on a full K computer without our help with 700,000 threads. So even normal users can use that tool on that scale. Okay, a little side thing, and I'm almost done. Yeah, like we had, like, I mean, people got kind of bored at our presentations because we talked about late senders and late senders and late senders and so on, because it was a nice, simple example. But then it was in 2014, there was a version of the Intel trace analyzer tool. I think it's no longer there because I can't find it anymore. But at that point, there was a beta, the 9 beta, and when you look at the description, they have now inside it, they have in the trace analyzer, knows for performance problems. And then when you look at it, they have late senders, late receivers, and so they copied our stuff into it without telling us. It's fine, we have a BSD free license, but they were so far basically to use the same patterns with the same names, and the diagrams look exactly like our diagram from our help. So it was really funny. So here's late receiver, weighted barrier, reduce, late broadcast, late receiver. I don't know what happened to it. It was like many people didn't use it anymore, so it looks like in the current version it's not available anymore. And that file, unfortunately, is no longer available. I might use the web archive to try to get it. Okay. Yeah, and then basically more or less my final slide is, we had a master student, and when he was finished, he made a cake. Unfortunately, he made a late receiver cake and not a late sender cake, but at least we had like once in a life, we had a late receiver cake. Okay, oops, okay, second to last slide. Again, the assessment, so I think Scorpy Scalasca, I mean, we started with Scalasca like 2006. We're still working on it. I have a whole team, 10 people working on it, other people in Dresden and Aachen also. It's a multi-institution, open source thing, and it's used and installed on many HPCs worldwide. And it's just installed, it's really used. So we use it as, I know that performance people on the site are using it. We're using it as part of a POP Center of Excellence. And what I really liked is what you said, the user interface with these 3 panes and the functions, how to use it, is consistent for 23 years now. Yeah, so it's like, everyone, I mean, you get a new, whatever, Android or something, and they moved around the buttons again, yeah, and you don't know why, yeah, it's still the same smartphone, the same functionality, but they want to do something, so they change the color from red to blue, and the button is round instead of square and stuff like that. Why? Yeah, so we really try to keep it, so like once the people understood how it's working, is there. Another thing, we got interest and we got even funding by Intel and AMD and partially Siemens to work on that stuff even. What that doesn't say is, you say, okay, it's the same stuff, yeah? It's just these nice free paints and I see it. What people totally underestimate is all the work to keep it this way, yeah? Like all the work behind it. So, and basically the team was always like 10 people. So I basically, since 2006, I have like almost 18 years times 10. So this is 180 person years of stuff, and it's not counting stuff outside Jülich, getting into this tool. So what does it mean? So first we had an internal system and we made it more scalable and working by using Scorpi, but a lot of rework had to be done. Then I don't know how many bugs we fixed in these 20 years. And we're going to tuning workshops where we basically use the tools to apply to, and we still find there's another user who does something who has never done before, and it triggers a bug. So you think that stuff was tested with so many applications now. Now there's users are really created using MPI in a different way or OpenMP, and we still think. And of course, like constant scaling improvement to make it work. But this is the thing which is really work, and you can't really write papers about it. Yeah, the stuff develops. Yeah, so extend your stuff to MPI 3 and 4. Yeah, OpenMP 3, 4 with tasking, 5 with target support. Now there's finally an OpenMP tools interface. So we have to rewrite everything here, the tools interface. Then I think no one has that. The Fortran 2008 MPI interface. The thing is, you want to have that, so when you use MPI on Fortran, it's type safe and everything is better, but it requires that you write your wrappers in Fortran. And everyone, of course, writes the tools in C. We are having a prototype, as I'm speaking, of that interface, of the main functions, point-to-point collectives, and so on. And with the next release this year, I think we were the first tool who basically will support Fortran in 2008 in Scorpi. This is another thing, yeah? I mean, when you look at all the tools, everyone claims I'm supporting MPI. This is true, yeah, you can, but how, like, do they support all functions of MPI 3 and 4, upcoming 5? Do they support things, and so on? And for us, it's a little bit more complicated. Most other tools just basically measure the time, how long the different functions run, and count them. But we have to, in order to get the patterns, we have to kind of implement all the connections, we have to track the communicators, the requests and all that. So we have to do more. You know? And then now, of course, we are totally busy of implementing GPU support, yeah? Because there's not something nice like MPI for messages, OpenMP for threads. It would be nice to have one thing for GPUs, but we have as OpenMP Target, OpenACC, CUDA, HIP-ROCm, Cocos, Raja, and the list could probably go up to here, yeah? Circle, yeah.
I'd like to mention one thing. So I think over the years, not only the scale of the systems increased dramatically, but also the scale of these programming systems.
Oh, yeah, the whole thing. Everything is scaled, the applications and so on. So there's a lot of things, and I still keep my 10 people busy, yeah? So that was the positive part. The negative part. Here. It's more future work in the sense we haven't done it yet, but that's what's currently not working with Scorpi, Scalasca, and so on. The thing is memory and vector, really memory analysis and vectorization analysis. You can not capture it just by software events. The only way to really doing it would be to get the suitable hardware counters, if they are available. But as everyone now is, every, not just processor, but every processor generation or instance has different counters. Yeah, it's not say, okay, we built a model of the necessary counters for Intel and for the AMD and for ARM. No, we would have to do it for Skylake and for version 1, version 2, and so on. So as an open source tool, we don't get the information fully from the vendors. And so Intel and VTune can do it for their processors, but an open source person cannot do that. Yeah? And so it's really, really hard. And then
what kind of performance analysis when you talk about vectorization?
It's the function vectorized or not, and you can do that by counting basically normal instructions and vector instructions and so on, and you can get a ratio, basically how much of the code would be vectorized and what of it, because we measure it for the different functions, you could tell, okay, this is, I mean, you can get from the compiler whether it was vectorized or not, but only from a runtime system, you know how much really basically, how much was used or something, yeah? And you can do some stuff. You can with vectorization not as bad, but especially all the memory stuff, you can only hardware counters. Okay, so it's hard. But the bigger problem I have is now all these more people go to task-based and asynchronous programming, also with the kernels and tasks, and it works best. You get the best performance if it's very loosely synchronized. It's not with block synchronized things. Yeah, but the problem is if it's these dynamic asynchronous behavior, you run it 3 times and get 3 different executions. So our whole model is I make a measurement, analysis, based on this analysis, I change it, run it again, just doesn't work anymore because you don't know is it coming from my thing and so on. The other problem is with asynchronous, like most tools, I mean, it's also Tau has this call graph display, HPC Toolkit is the same thing. They try to splice the stuff into the call tree, but if it's really asynchronous, this inclusive-exclusive doesn't work anymore. And we try to kind of get it in, and what we do is in Scalasca, in Scorpy, is basically you have the main call tree, and then for each separate task or kernel, you have a separate call tree underneath it, and you know, oh, here it's launch, but it's, you miss the big picture. So, and we struggle for that for 10 years, and other people too, and no one so far has a good idea how to write a good, nice performance tools which gives you a high-level picture with good metrics for this asynchronous behavior.
Let's talk about call trees again.
We might, yeah. But the thing is, it's basically, my personal thing is, we came, like all the people who worked on these tools, I mean, it's just crummy. I mean, we all work on that. We have this old history, and we have all these synchronous history. So I think we need a new guy, a new PhD guy with no history information. Perhaps like he has the right idea how to get a great tool. But I am happy to discuss that and anything. So I think now, I mean, we'll have another 10 years of MPI and OpenMP and simple CUDA. So the tool will be helpful another 10 years. But I see a limitation. Yeah? And then the whole thing about C++ and Python. I mean, the thing is, with data analytics, people are not programming their simulation anymore. They're using frameworks. Yeah? And you can do analysis, basically, how to parameterize this framework to run it faster. But analyzing which function of that framework is, for a normal user, is useless. Yeah? It would be helpful for the framework developer, but not for us. Yeah? So there's less and less people be able to use the tools. And also, I mean, it's Python, and when they don't use MPI anymore, yeah. Okay, so that was basically a lot of stuff. It summarizes like 37 years of working on different things. I hope it was a little bit interesting, and it sparked some discussions, I guess. And yeah, and I thought it was a productive. I know I sound like I retire almost, but it was a productive work so far, and I have 2 more years before retirement, or 3 years, sorry. So thank you. But I think it's time to pass it on to younger people. Okay.
So I think you're right. Intel took over quite a bit of that years, right? And
C lab, we actually started to use VQ on our Supercomputing machine. And it's really a great tool, and it follows this approach that you have bottlenecks and you say highlight what is a more important bottleneck, is it memory, is it bandwidth, or is it latency, and so on. So
but the problem is, it only works on Intel.
Exactly.
Yeah, and the second thing, it only works on one node.
No.
You can multiple, but it has no really like nicely pulling it scalably together on 1,000 of nodes.
But otherwise, I think it has this drill down approach through these bottlenecks.
Yeah.
You can learn about the pipeline, where you use time in the pipeline. And it's not like you really have to understand all these little tricky details of the numbers, but they try to show you what is the
No. Yeah.
And, so I think that is the best tool I know that actually follows this approach that came sort of out of apart, I would say.
Yeah.
Maybe there are others as well.
Yeah. Okay. Yeah, so thank you. As I said, we have more time in the rest of the week to discuss that.
I think it was a great presentation.
Thank you.